In the last video, we left with a little bit of a cliffhanger. We had an experiment where we were looking outside of, for instance, the university and looking at people passing by. And they were either in a car with a probability of 3/10, on a bicycle, a probability of 1/2, on foot, a probability of 3/20, and a probability of something else, it's 1/20. First, we thought if we had a simple coding of 00, 01, 1011, and we would send this to a friend on the other side of the world, this would be probably the best way. However, our entropy showed that we could actually do it way more efficient, because the entropy always says the most efficient, on average, possible way of bits. Today, or in this video, we're going to look at how we get through that coding. And that is done with Huffman coding. Huffman coding, which was named after David A. Huffman, who lived from 1925 until 1999. He developed this coding to obtain the most optimal one, or optimal one thus far, and goes as follows. First, you write down all the probabilities in a descending order. So we have 1/2 for bicycle, which is the largest. Then we get 3/10 for cars, 3/20 for on foot, and 1/20 for something else. Now, the first step, what you do, is that you connect the two lowest probabilities. And if there are multiple ones, just pick the lowest ones, or just two, it doesn't really matter. And we add those probabilities up. So here we get to a probability of 4/20. Now we do the same thing. However, we are disregarding 3/20 and 1/20. We are only looking at this, and this probability right now. The lowest ones are 4/20 and 3/10. So let's combine those two. So we get a nice tree. This value added together will be 5/10, or 1/2. And now we have only two probabilities left, so we can add those together as well, which will result in 1. Great. Now what? For every line that we've drawn that's going upwards, we will write down a 0. A 0 here, a 0 there, and a 0 there. For every line going downwards, we will write a 1. 1 and a 1. Now, we can create our coding by walking from the top of the tree, from this point here, downwards. So let's make a table. We have our code. We have how many bits are in the code, and the probability that is associated with this code. The first code is just 0. How many bits does it have? 1. How do we know it's just 0? Well, we start from this point and we go to 1/2, and we see we're just passing by 0. So this is the probability of 1/2, just a 0. Now we're looking at the next one. We walk down the line, we see a 1, and then we see a 0. So we get 1, 0, has 2 bits, with a probability of 3/10. The next one, we see that we get 1, 1, 0, so we get 1, 1, 0 here. It has 3 bits with a probability of 3/20. And the last one, we see a 1, and a 1, 1, 1, 1, with 3 bits and a probability of 1/20. Now, we have two codes that are actually 3 bits, while in our original everything had 2. However, this is still more efficient. And we can calculate that, because we can calculate the expected number of bits that are sent on average. And for that we need this table. We are going to calculate the expectation of the number of bits sent with this coding. An expectation works the same way as in probability theory. What we are doing is we are summing over all possible combinations, or not combinations, every possible pair of probability multiplied with the number of bits that it takes for that probability. So let's do that. We have the probability of a half times 1. We have 1 bit for this probability, plus 3/10 times 2, because the probability for 3/10 only has 2 bits. The same can be done for 3/20 and 1/20, which also has 3 bits. If we calculate this, then our average bits per message sent, not per message, just the average number of bits that is sent, is 1.7, which is already better than 2. And that is because the probability, the outcome that we send the most, only has 1 bit in it. So we need that one to be the least bits as possible. Furthermore, you could say, well, then for the other ones, you could also make a for this one and this one, you could make a different code. Let's say you could make for this one maybe 0, 1, and for this one you could always also make a 1, for example. But the problem with that is, if I send you 1, 0, how do you know that this is not actually something else and a bicycle, or that this is just a car? You do not know that. And that is also something this Huffman coding provides, is that you can concatenate every code behind each other and you can still know what every is. There's no ambiguity in, maybe this code could be these two or it could be this one. That is impossible. And if we compare this value with the entropy that we calculated in the last video, which was 1.6477, we see that this is not super optimal yet, but this is very close, and this is already good enough to be satisfied, because sometimes it's very difficult to get the exact expectation to be the entropy. However, this is getting very close, so this is still fine. And that is how you obtain the most optimal coding for a probability distribution, to make sure that even when you think the original coding is efficient, that you can even make one that is way more efficient, because you are taking into account the probabilities of each code separately.